Okay, so in this video I want to talk about the double complex spectral sequence. And the spectral sequence from a double complex is one that often comes up, especially in algebraic geometry. So this is an important example, and I think even in algebra and algebraic geometry, people tend to think of, well, most spectral sequences come from double complexes. But really we're going to see that this is a special case of the spectral sequences that we already know and love. So let's see how this arises. I'm going to try to set things up nicely so I don't have to worry too much about convergence. We'll deal with the more complicated stuff in the future. So I'm going to let C be a double complex, but I want to make sure that it's a first quadrant double complex. So I think I said that in the last video, but maybe let me be really precise. CPQ should be 0 if P is less than 0 or Q is less than 0. Okay, so this, I would draw my picture in the normal way with P on the horizontal and Q on the vertical, and it would show up in the first quadrant. And the claim is that in this nice situation, that then C gives rise to a spectral sequence. And, oh, I should have said, sorry, a first quadrant spectral sequence. Maybe that's kind of obvious, but let's be precise here. Okay, so a first quadrant spectral sequence. And really what's sort of neat here is that we're actually going to see we sort of, in a, I don't want to say natural in the mathematical sense, but we kind of, in a clear way, get actually two spectral sequences. And then the common game here, and I've referred to this a little bit before, is, well, okay, we want to filter C two ways, and then we know how to get a spectral sequence from a filtration. So that'll give us two spectral sequences. And then, but the common game here is to play these off each other. So we had a question the other day about how do you figure out when you have non-trivial extensions or when you can't figure out a differential or something like that. And one of the main games that I would play is come up with a different spectral sequence that does the same thing. And when we have a double complex, we sort of automatically get these two options. And we'll see some examples of how you might play those off each other. So the first thing we'll do is filter by columns. Okay, so what does that look like? Well, I want to define somehow a filtration on my complex. So I should have CPQ, but I'm going to call this call less than or equal to n. This is not standard notation at all, but the standard notation, I can never remember what's what, so I'm going to make up my own. So we've got that this should be CPQ whenever P is less than or equal to n. Remember, P is our horizontal grading, so that's going to tell us that we're taking columns up through 0 through n, and then we should have 0 else. Okay, and so what might that look like? I think you can imagine, but I've got P and Q, and so I've got some stuff here maybe. I'm just drawing dots because there should be some R modules or whatever. Okay, and then I have zeros everywhere else over here. Maybe let me give myself some more stuff. Extend that a little. Okay, so this should go up through degree n. And then this will, of course, fit inside the filtration in degree n plus 1. So maybe, I guess that sort of looked like 3, and maybe this looks like 4. Okay, and then zeros everywhere past that. And so that'd be n plus 1. And okay, so I want to take this filtration on the columns, and then what am I going to do with it? Let's let Fn call. Again, this is not standard notation, but this helps me remember. I'm going to take the total complex of this filtration of my double complex. So I look at C star star, but then I only take the nth filtered piece, okay? And this, maybe not immediately, but we can see that this does filter our total complex. So we've got 0 sits inside, and then this Fn call, so the total complex of this piece we've got here sits inside the total complex for the n plus first piece, and so on. And if we kept going forever, then of course we would get everything. And so yes, we have filtered the total complex. And I think it's kind of helpful to remember sort of how we're taking or what's going on in here. So remember, at any given spot, there's these horizontal differentials and these vertical differentials. And that's true over here too, and really at all of these spots. And then we're taking, for our total complex, collecting up along the diagonal. Okay, great. So this, as always, this filtration of a chain complex gives us a spectral sequence in the usual way. And maybe I'll say it's E1 page, but I'll denote call. So I remember that this is the E1 page for this column filtration. Well, as always, it should be homology, HP plus Q. Notice I'm doing this all homologically graded, so I really do mean homology. You could, of course, do this co-homologically as well. And I don't know why I'm writing Q. Okay, so I should take the homology of the filtration quotients, and this should cook up for me the homology of the chain complex. Well, what is that chain complex that we filtered? It's this tote C. Okay, so I want to unpack this a little bit, and I've written large, so I can't really fit it all on the screen. But great, there's a spectral sequence, but what does it mean? What does it look like? Well, let's look at one of these Fn mod Fn minus 1s. So when I look at that over here, right, I should have quotiented out all the stuff to the left here. So notice my horizontal differential crosses that boundary. So this differential, which goes horizontal plus vertical, the horizontal stuff always goes to 0. And so I really just have this vertical strip right here, and with its vertical differentials. Okay, so just write down, this is just the vertical chain complex. And that looks like Cn comma star, right? That second thing tells us about the height. Okay, so when I look at the homology of that filtration quotient, well, in each spot, I'm really just taking the homology of my total complex with respect to only the vertical differential. Okay, maybe I shouldn't call it the total complex. I just mean I'm taking the homology of each of these columns, which are just these singly graded chain complexes, and I'm only using that vertical differential. Okay, so what's nice about that is that tells us not, what am I trying to say? I'm trying to say, you know, in the Sayre spectral sequence, we had some filtration, but what we really had was a nice E2 page. And what this is telling me is that I can actually backtrack and get a nice E0 page, which is kind of a different way to go. So what we could do is just let E0 PQ be well, CPQ from our double complex, and then have our differential on the E0 page just be that vertical differential. So what would that look like? We'd have E0. Maybe I should make that bigger. Okay, so we'd have some stuff from our double complex. And we'd only be looking at the vertical differentials. Okay, we'd take homology. I think this should be D upper 0 is dV. Okay, we take homology and we get the E1 page, which is actually the thing we knew how to describe in the first place, just coming from, we filtered a chain complex, and so we always know what to do there. Now these dots are not the same as the dots on the E0 page, of course, because I've taken homology, but I just mean there's stuff there maybe. And now what are we left with? Well, what's our D1 differential? Well, we're still in this double complex, right? We've just taken homology with respect to the vertical differential, really because we were looking at filtration quotients and quotienting out by all the stuff that was horizontal from our spot. So what's going to happen when we do this D1? Well, what differential are we left with? Only the horizontal. So I'm going to say equals DH. Of course, really I've taken homology, so it's not exactly the same. These aren't even the same groups, but I think it's almost sort of clear from the picture that all we're left with is this horizontal differential. If you actually start chasing that through the diagrams, then you can verify that, but it's a little bit of a messy chase. So I'll leave that as an exercise if you're interested. That didn't look any better. Okay, anyway, so then we take homology with respect to that, and we get the E2 page. And now, remember, how did we figure out these differentials? This came from writing down our unraveled exact couple and chasing things, and we saw that our differentials on the E2 page, at least in homology, went over to the left 2 and up 1. Okay, and maybe I don't have a nicer description than that, but let me say there's the usual spectral sequence. So all I'm trying to say is if you sort of ignore this E0, this is your usual homology spectral sequence starting on the E1 page, but what sort of, told myself I should write those as upper and then I didn't. What's sort of miraculous here is that actually we can go back to E0 and say, you know, that's really just our double complex, and ignore part of the differential, only take the vertical. Okay, and so then what we often do is abuse notation a little bit and say, well, what did we do to get to the E2 page? Well, this is really, we took the vertical homology of our double complex, so just with respect to only the vertical differential, and then we took the horizontal homology of that. Now, this is a little bit of an abuse of notation because, of course, it's not exactly the same stuff there anymore, but basically we just want to think of, use the vertical differentials and then use the horizontal differentials. And then I think describing the differential on the E2 page is a little bit complicated. As I said, I would want to go through the unraveled exact couple and chase things around. But, you know, as with the Sayre spectral sequence, we just say what's on our E2 page and then what does it converge to. And we know we filtered the homology of our total complex, so this should converge to the homology of our total complex, and indeed it does. Okay, and we have this nice convergence when we're in this first quadrant case, so that's why I set us up that way. Okay, well, maybe version 2 is that we could also filter by rows. Here's what I was trying to say. There are sort of two natural choices, but I don't mean natural in any type of precise mathematical sense. I just mean once you think of columns, you might think of rows also. Okay, and so how would we do that? Well, if we want to filter by rows, then maybe we would define C row PQ, where the row is less than or equal to n, to just be, let's take CPQ as long as Q is less than or equal to n, and 0 else. Okay, and so now, just to have a visual, I like having a visual. So I've got P and Q. So now here's my N, and everything should be 0 above that. And then that should include into my filtration for N plus 1. Of course, these could go on forever to the right. I'm just trying to draw a little piece. And then maybe it's 0 above that. Sorry, not 0 above that. We're defining it to be 0 above that. Okay, and then we can set up F and row to be the total complex of this truncated double complex, row less than or equal to n. And this again filters our total complex, and so we're going to get a spectral sequence. Now here the differentials might look a little weird, and so sometimes people start with the transpose so that the spectral sequence sort of moves along in the usual way, but let's not worry too much about that. The point is that we now have another spectral sequence where I'll call this one row filtration. People usually just call these first and second filtration, but then I can never remember which one's which. So using this filtration on the rows, well, how would we compute homology? We can make basically the exact same argument and say that we should take the vertical homology after we've taken the horizontal homology, and notice the order now is switched. Okay, so this is exactly the opposite of the one I had before. So I just want to use my differential, my horizontal differential up first, and then once I have that, what's left? My vertical differential, and then, okay, it gets a little bit messier and I need the full power of the spectral sequence to keep going, but there is a spectral sequence that converges to the homology of the total complex. Okay, so we've seen that we have these two versions of this spectral sequence, and they converge to the same thing. And so that's what we want to do. We want to use that next to hopefully learn something. Okay, so, but this is the spectral sequence for a double complex. And again, I said the spectral sequence, but I really mean these sort of two obvious spectral sequences that come from a double complex. And notice they came from a double complex, but what did we do to come up with a spectral sequence? We filtered something. So it's really all going back to that same machinery of having a filtration, getting an unraveled exact couple, the usual deal. Okay, so let me stop this video and pick up with some applications in the next one.